I want to represent a great work that has been carried out in our university in collaboration of an Open Book Foundation. Anand Fabulous SOC, uh, in collaboration with JNTUA and Open Book Foundation, we are developing a Fabulous SOC, and there are many contributors behind this a great work. Yeah, and this Fabulous SOC is indigenously developed for academic R&D purposes. Used for, and we have a plan regarding there are the stages where we want to develop our Fabulous SOC named of an Anant. Actually, the proposal of an Anant starts in collaboration with JNTV and Open Foundation. And at the first stage, we want to develop Anant 1.0, where we are developing all the peripherals, designing development of many peripherals connected to the processor, and an application level testing. And at the second phase, like Anand 2.0, performance enhancement, integration, verification, validation, SOC level testing, all those processes will be carried out. And in third, Anand 3.0, there will be in board level mapping and addition of many more peripherals and FPGA porting, hardware validation. And we can extend this the stages up to the level what we want to define our Fabulous SOC. In this regard, we cover details about the design of an SOC that is compliant to an A2O core, that is an open power processor, and to develop these designs using an HDLs, and to develop the peripherals that are connected to processor via an on-chip bus, that is an AXE4, and peripherals like SPI, I2C, PCIe, Ethernet, DDR3, and flash memories like NAND and NOR and DMA have been used. Uh, this shows an SOC architecture where we have an using processor A2O core and all the peripherals PCI, SPI, I2C, DDR, memories, DMA, all are connected to an on-chip bus AXI4 where L2 acts as a local memory. Here, the processor A2O core, it has a high frequency and a four-threaded design, optimized for throughput and targeted for an 3 gigahertz 45 nanometer technology. And it's an out-of-order pipeline supporting for 1 to 4 threads, and it's a fully support for Power ISA 2.07 using Book 3E. And the core was also designed to support most like a pluggable implementations like an MMUs, matrix math units, and an auxiliary units AXUs like logic macros. And this includes the elimination of an MMUs using ERAT only used for uh, like translation or in protection in that way. And also here we have an that 4 by 32 64-bit general purpose registers in support both little and big Indians, during like and also here we have an two caches, I cache and D cache, which will be support of 32 KB each, which has a four-way multi-threading, and it has an BPUs of an 8 and 1024 entry branch history tables. And this L1 caches is in 32 KB each, I cache and D cache. It's 8 ways it associate to data cache, and a 4 ways it associate to 32 KB instruction cache. And it's execute a simple out of order capable issuing two instructions per cycle. one to the 6 stage arithmetic ALU, and one for the optional AXUs like auxiliary units. And here the compliance is like it's an power ISO 2.07 that will need to update the compliant with either the version of 3.0c, maybe an power ISO 3.1 contributed to the OpenPO Foundation by IBM. And there may be in Radix translations and to eliminate non-compliant ones and missing required for a given compliances level. This is a brief about the processor A2 core of an IBM OpenPO Foundation and IBM. Now I want to share some details regarding the AXI4 on-chip interconnect that have been used. It's an advanced extensible interface, and it's an on-chip bus that is directly connected to an IBM processor A2O, so that the processor can communicate to each and every peripheral through the bus, and it enables a higher performance either with existing bus architectures, and also it has been comes under the category of an AMBA 4, the most common bus architecture in modern complex SOCs and FPGAs. Here, the peripherals connected will be selected using an FSM methodology. Mostly, this AXI4 will support up to 16 masters and 16 slaves, interfacing with single master and single slave talking with each other at a time. This AXA protocol is suitable for higher bandwidth and provides a higher frequency of operation without using any complex bridges, and meets the interface requirements of a wide range of components, and is suitable for a memory controllers with a high initial access latencies, and it's backward compatible with existing AHB and APB interfaces. Here, these and also it has some channel handshaking mechanisms where it has invalid and ready in all the 5 channels. At here we have the 5 channels: write address channel, write data channel, write response channel, and read address channel and read data channel. From the source, we have an valid to indicate when valid data is available, and in the destination, it uses an ready signal to indicate that data is accepted. For read and write, we have a last signal that is to indicate the last data transfer in the bus that is taking place. Here we have blocks that have been analyzed, the design will have an FIFO and a write channel, read channel, and we have separated the memory controller. All these blocks are will communicate simultaneously based upon the master that have been selected using an arbiter. In this, we have in burst-based transactions in order to simplify the design, generate in a slave, maybe that is allotted to a slave in 4 KB unit term, as the slaves must not cross the 4K boundary. Like master just ignores the read data here. And also in burst, we have 3 types of burst, like a fixed burst, incrementing burst, and wrapping burst. In a fixed burst, we have address that is remains constant in a burst. It is suitable for FIFO like designs. And in an incrementing burst, we have like a transfer size. It is usually suitable for a sequential memory like devices. And coming to a wrapping burst, here it must be aligned and burst length should be 2, 4, 8, and 16. It is well suited for a cache like refills. Here, after the transaction, we need to have some responses. That response is like okay, like everything is okay. If it is an X okay, exclusive access is successful, and we have a slave error if FIFO is underflow or an overflow, and in a decode error, no slave present at that address only if there is a reach here. This master and slave are compliant to each other, and here we have the features like it has separate address and data phases over 5 independent channels, and also it supports for an unaligned data transfers, and it's a burst-based transactions. The separate read and write channels that can provide a low-cost DMA. Supports for multiple outstanding addresses and an out-of-order transaction completion. We have the signal dependencies coming to in a read transaction. Uh, are valid and are ready. It's an option, but it can wait for the validation of my data. These both are valid and are ready must wait for are valid signal so that the next processing are ready. It's an optional one. It can be wait it or it may not. In a read data transaction, a W valid and an a W ready and W valid and then W ready. These signals are then optional. They can wait or they may not. But after W valid, they need to wait for B valid. Means like it need to have some response from a slave. And for W ready also, it must wait for an B valid signal. B valid, and after that B ready will be accepted. So these signal dependencies are used to avoid and like a bottleneck issues in an the protocol that have been the signals that have been accepted. This is the AXI4 design generated in a Mentor graphics tool and an AXI4 interconnect that have been interconnected to an A2O processor core. Then that AXI4 design, and this is an view AXI4 design integrated to an A2O core. This RTL, like a block that is representing. There's the simulation waveforms for a fixed burst type simulation and an wrap burst type simulation and an increment type burst simulation. And like we have another peripheral, Ethernet. Actually, it describes how the network devices can format and transmit the data. Ethernet, it's a, like the competing technology of time, such as an IBM's token ring. It is compared to. And Ethernet, original 10 megabits per second throughout increased tenfold to 100 Mbps in the mid 90s. But the current versions of an Ethernet can support up to 400 gigabits per second. This Ethernet MAC module in the device implements a 10 or 100 or 1000 Mbps Ethernet MAC. This is compatible with an IEEE 8 or 2.3 standard. This also supports MII, RMII, GMII, RGMII, and PHY interfaces to support like several automotive applications. Regarding the features, these Ethernet will supports 10 Mbps, 10 megabits, or 100 megabits, or 1 Gbps operation, and full duplex supports for 10 and 100 Mbps mode, and an FIFO interface to user application, and also it support burst frame generation and termination, transmitting frame source MAC address insertion and receiving frames. uh, this transmission algorithm and then receiver algorithm, how the transmission will be taking place from the receiving broadcast frames throughout the constraint and transmitting frames source through MAC address insertion. That's an optional one. Here we have in frame format the frame check sequence field. It's a 4 octet, like a 32-bit cyclic redundancy check value. This value is being computed as a function of the contents, where like address, destination address, type, and data, and also whether it's an invalid frame is there or a valid frame is there. We need to check at least one of the following conditions. We need to check whether the frame does not have an integral number of an octets in length, and the bits of the incoming frame exclusive like FCS field shift. It do not require generate a CRC value identical to one received one, and the frame length is shorter than the minimum frame size. We need to check all these conditions. And regarding to an architecture where we have an TCP, MAC, and GMII, RGMII, and SGMII. In a transmission control protocol, it enables application programs and then computing devices to exchange messages over a network, and it is designed to send packets across the internet and a successful delivery of a data and the messages. Also, like representing a MAC, it is responsible for Ethernet frame protocols, and also an error detection of these frames can be connected to any type of a physical layer. In gigabit media independent interface and media independent interface, these are all the parallel interfaces connected to MAC to the physical sublayers. And then reduced gigabit media independent interface like RGMII. It's an alternative to an GMII, over an 50% reduction in the pin count compared to an GMII. And also there is a combination of a physical coding sublayer PCS and then like physical medium attachment and the physical medium dependent. A sublayer compresses the physical layers of all this Ethernet protocol. Like coming to like block diagram in Ethernet, we have an a transmission buffer block consists of an 2K byte dual port memory to hold a transmit data for one complete frame, and then transmit interface control register. And then at the receiver block, we have a buffer block. It contains of a 2K dual port memory to hold receiver data for one complete frame, and the receive interface control register. And the transmitter block consists of an transmit logic, cyclic redundancy check, CRC, generator modules, transmit data marks, and then transmission first in before, transmission before, first in first out, and then transmit interface module, and the CRC generator module that calculates the CRC for a frame to be transmitted. And also we have an MDIO master interface block that is included in the design if the parameter enables MII management module that is injected in the Vivado tools. Um, by having these blocks coming to an receiver block, it consists of an RX interface, loop back control marks, and then receiver FIFO and CRC checker, and receive control module, and then receive data signals from the PHY that has been passed from an loopback control like marks, and that is stored in an receiver FIFO. Here we have an a speedy like gigabit of an 1 Gbps. It is speed ranges from 10 times faster than the Ethernet, fast Ethernet, and it's a full duplex one, and it is capable to connect the systems in Ethernet that need to be strong to noise, and as it is strong to the noise, the standard of the info transfer doesn't degrade, and the transfer quality is also good. And also the application of a reusable IP module is increasing due to the increasing demand for embedded systems. So Ethernet interface IP has a great potential for a vast range of an applications that require an internet connectivity, and peripherals and devices that have been will be made internet ready in the future. Coming to simulation waveforms, this is a like Ethernet controller that have been generated in Metagraphics tool. These are the like a slave mode transmission results where we are transmitting the data from an application to some on the slave where it is targeted. As if from the master mode we are sending a data. And coming to an I2C, it's an inter-integrated. It's a short distance serial communication bus. It is one of the dominant bidirectional and half duplex protocol for communication between a master and a slave devices, which uses two wire for communication, like serial data line and then serial clock line. The I2C master controller transfers the data between the master and the slave It's an low bandwidth for onboard communications, and it has designed a unique address. Here these AXFO sleeve interfaces with the AXFO bus and an I2C controller. The controller performs only the read and write operation at a time because it's an half duplex protocol. And also here we have some status, control, demand, control data, and prescaler registers we are using here. It also has a design features like 7-bit addressing and an 8-bit transfer data, and also support for single master and multiple slaves. And a master and slave both can operate as a transmitter or a receiver. And then design supports both an AXI4 and an AXI4 Lite interfaces. Coming to an like a data flow, how the data from the I2C master, the data transfer is data is transferred from the master to the slave based upon the commands registers, that is a start, the read or write, and then stop commands that have been used. We have a status register, control register, and prescaler register which have been used in this. And the communication proceeds whether the master and slave on the data bus both can receive or transmit data depending whether there is a read or a write bit. If there is an acknowledgement low, then if it is no, then it is continue to send the data. If it is yes, then it will go to an ideal bus state. And coming, if it is if the read data bit is 0, if it is yes, it goes to and write data to slave, or else it will be an it will send an 7-bit slave address followed by an read bit, and then the read will be going on and getting ready for the next address to be read, and then the simulation will be stopped. In this way, the operation like the master, the which generates a clock signals, initiates a transfer, means like we have a start condition and then terminates a transfer. It's a stop condition, and it may also act as a transmitter or a receiver. Coming to a slave, addressed by a master, the device that is addressed by a master, also it acts as a transmitter or a receiver. We are having an I2C like a data frame formats start address, starting, addressing, and acknowledgement or non-acknowledgement data, and then stop bits we are indicating. When we are using a start and a stop bit condition, with respect to an start condition, if the serial data acknowledgement is 1 to 0 transition, then serial clock line will be a 1. And if it is stop bit condition, then that SDA will be 0 to 1 transition when SCL is 1. And the bus state, like if it is busy after S and before the next step, that is P. If it is free, then after the positive edge and before the next slave that is activating, it's a start condition and then stop condition before start and stop conditions. And we have a data validity if it is a valid data, or the data is not. If the data on the SDL line must remain stable, that during a high clock cycle to be a valid one. Here it shows in the simulation results where we observe all these on the start and stop bit condition data validity. And also with respect to an AXI like AW valid, AW ready, W valid, and W ready, AW valid that have been accepted. We can observe in the waveform. After integrating to an AXI4, you are getting this simulation. For read transactions, AR ready, AR valid, R valid, and an R ready. They must be an accepted high when address and data will be received from a slave. This is an A2O after integrating to I2C after integrating with an A2O core. Here you can observe the integration with an A2O core, like indicated with another color line.
Hello. Hi, everyone to all. Uh, Kindly anyone check whether my audio is perfectly fine or not. Hello.
Yep, we can hear you.
Yes, sir. Thank you. So myself, Sharan Kumar. We are also teammates, whole teammates. So me and Venkatesh is going to present this. So Venkatesh has discussed till now the Axi part and one or two of the peripherals which we have actually integrated with this Axi and A2O core. So now we'll quickly go through the remaining peripherals, all those things. So we'll talk about the non-flash memory controller, which is a replacement of a traditional EEPROM, and in the hard disks for this low cost and versatility. So because of the differences in the structure of interconnection in the memory cells, the NOR flash is also known for it, the random access capability. But NAND and NOR applications will be different and unique. So they will be known for their own unique compact sizes. So this in general, this NAND flash will be accessed one page at a time, and arrays can be done as per the block basis. So this is a NAND controller architecture which we have implemented in this fabless SoC. So the main logic of this NAND controller will be depicting in this four FSM blocks, like a register, and main logic will be depicted in this block. And there is a timing FSM as well as main FSMs, which will be carrying through the all slave and master configurations, whether it is write or read, or with respect to page or with respect to block and everything. So here there is a NAND flash memory. Actually, with the help of a physical memory, we can also check with this. So this is the block diagram with the Axi interconnect, which we have actually implemented. This is the one. This NAND controller supports page program and page read as well as block arrays and read status, reset, etc. All those things. So these are the some of the design features of this NAND flash controller, which actually support the 2 GB capacity. So all program and arrays actions will be supported by the read status. And we'll be seeing all those in the simulation waveforms, actually, which we carried through the Axie4. And this is a page program. That means this is similar to the writing to the memory address location. So whenever it starts with a page program operation, the write command will be 80H. These commands will be based on the data sheets which defined by the manufacturer itself. First, we'll be driving the two column addresses and then followed by the row addresses. Then those will be looping back to 0 to 2047 since it is a 2 GB memory controller. So that is the thing. When the loop ends, then again there will be command for controller to whether it should be wait or to continue the operation. If it continues to further write operation, then there will be a command like 70H way to actually place the data. So in this, there will be three main signals like AW valid and W valid, and from the controller side, this is like a NAND flash memory read or BC. These will be checked and then the operation will be performed. So similar to the page read operation, actually the write command start from 00H, which is different from the page program. So here also the two column addresses and followed by the two row addresses will be sent, and then there is a write command which is at the address location 30H, and similar fashion will be followed at the read also. So when it comes to the read operation, the handshaking signals from the Axie on-chip bus will be like address read valid and read ready, and with the help of this NAND flash memory read or busy ready or busy, this also can be integrated and carried forward to the further operations. This is the page program, which is similar to the write operation. If we want to do the write operation, this NAND flash memory write enable will be active high. Then only the write operations will be carried. First, controller will be sending in command with 8-bit, and then it will be followed by the 5 cycles of column and rows. Which we have seen like a 2 column and 3 address will be there. So it takes 5 cycles. In each cycle, one column address and one row address will be sending. So this is the simulation results when it comes to the page read. And in the similar fashion, the 5 cycles will be after the 5 cycles, we'll be checking like this NAND flash memory read enable line. If it is active high, then the controller will be depicting like it is ready to read from the memory, which is actually written in the previous cycles. So these are the from NAND side. So when it comes to the NOR flash memory controller, this has a configurable address width from 1 to 32 bits, and this NOR flash has a capacity of 1 GB. This also supports like page programming and reset, and as well as a page read, and with along with that, chip erase function also has been implemented in this NOR design controller. So this is the architecture which is having several predefined registers. With the help of these only, we are performing all those main FSM logic. There is a sector address register which will be storing the most significant bits of the address which we are providing from the AXE4. So then there is a other address register. The least significant bits will be storing here other address registers. Then there is a actually code register. That means for each and every operation, there is a perfect code, and when the code is getting selected, then that particular operation will be going to trigger. That will we'll see in the next slide, like in the form of a FSM. So then there is a receiving data register, which we will be storing it in a buffer so that there won't be any loss of data. So then there is a ready or busy register. So with all these registers will be combined with one single module, and then that will be carried forward to the control FSM, which will be actually taking care of all these operations. And then with the help of flash timing, which actually depicts the timing FSM, which is almost similar to the NAND flash memory controller. But when it comes to the design features and all those things, then there will be different type of architecture which we have to take care in the timing FSM. So in both sides, on the one side, we will be having like NOR flash memory, like physical memory card, and on another side we have AXE slave interface, and which is further connected to the AXE4, and this on chip will be connected to the A2 core. This is the memory controller FSM, main FSM logic. Here, if we want to do read or write operation, then we have to first write the address, whatever we are driving, into the sector address register, which show the MSBs, which we have seen in the last slide. And then if we want to read it, first of all, then this AXE code 0101 to be sent to that particular address. When this code has been checked by the FSM, if it is correct, then the read operation will be performed. Else it will go to the ideal state only. In the similar fashion, if we want to perform the program or write operation, then this 011 code will be helping in that. For each and every case, this ready or busy signal, we will be checking what is the status of this. Whether it is active high, then only the particular operation will be carried through this FSM. So as in similar to this page program and read, remaining reset, as well as sector erase operation and chip erase operation, and this control ID, everything will be depicted. So main difference between the NAND and NOR is like in the NOR, there is a particular address which is mentioned in the starting of the operation itself. So that is one thing. So now when we come to the page program operation, which is similar to the read operation actually. So if we want to do the write operation. Sorry, write. It is a write operation. So the three main signals from this NAR flash controller will be like chip enable, and one thing is like a write enable, and the one more thing is like a output enable signal. So if the chip enable is low and the write enable is also low, then that particular operation will be carried for the write operation. So all these will be taking care of these signals, and this is a DQ will be the buffer which is actually storing the data from the read side. So then if you this is a page write operation. So here also the chip enable will be low, and then the output enable will be low, but write enable will be high here. So this is the only difference between here simulation results of NAND and NOR. So now we'll move to the DDR3. So this is a third generation actually which we have implemented, and this third generation DDR3 controller has a high speed synchronous dynamic random access memory technology, and the data transfers between this double DDR will be active at the both the edges of the clock. I mean, like positive edge as well as negative edge, which is like depicting here. This controller serves as an important bridge when high speed data transfers will be taking place in the architecture. So when we come to the architecture of this DDR controller, the main logic controller will be implemented and segregated into the three parts. Like one is completely dealing with the CDC as well as STA. Whatever the clock domain crossing issues like metastability, data incoherency, and all those things will be implemented in this block. And then there is a bank management, which has 8 banks in this DDR architecture. And there is address and data control logic also, which is implemented in this controller logic. And in the same way, like NAND and NOR, there is a DDR3 memory if you want to test it physically. And another side, we are having this AXI 4 as well as from the code. These are some of the features for this DDR3 memory controller, which is having like master as well as a slave configuration of AXI 4. And one important thing is like it is having a self-refreshing mode, and it even supports the power down control and the newly implied reset pin. This is the design flow which is followed for all memory controllers. And first, we have taken the specifications from the data sheets as well as some of the IEEE papers. So then we have carried out the design in the form of hardware description language in Verilog. So after that, the wrapper has been generated to integrate with the AXI. And then if at all any errors, we are going for the debugging option and checking the wrapper again, and all those things will be carried. And at the end, this whole block is will be integrated with the A2 and functional results also has been out like so. These are the write operation for DDR3 controller based on AXI 4. All these will be getting perfectly fine with respect to NAND and NOR. So this is a read operation from the DDR3 controller. See, now we'll move to the some SPI and PCI and the remaining peripheral. SPI is a serial data transfer line. This design has been carried out based on the Motorola's version 3.06 design. So the serial data line which is having in this SPI is operate in a full duplex mode, and there are 4 different types of clock polarities and as well as the 4 clock phase modes. So whatever the SPI module we are having, this consists of several blocks like control registers as well as data registers and status registers to tell that how the actual controller is getting depicted, whether it is a busy or transferring the data or reading the data and all those things. And another important thing is like it has even a baud rate generators, and then port logic also has been implemented in this SPI controller architecture. And the same way, these are the output and input ports from the controller block, and there is the transmission and receiver FIFO. Whenever we are carrying to the multiple signal operations, so we'll be having like a FIFO kind of thing. So this is the architecture. And when it comes to the operation, as we have seen that there are two different modes which have been implemented in this. One is like a regular SPI mode, which will be having different select lines for each and every peripheral. But when it comes to the daisy chaining mode, with the help of only single select line, we'll be operating all these slaves based on their request, and priority logic has been implemented in the SPI controller architecture. And this MOSI, which actually depicts like unidirectional signal, which is used to transfer the data serially from a slave to the master. But when it comes to the MISO pin, this is also a unidirectional signal, but it transfers the data from master to slave. That is the thing. This SS line will be used to select the slaves, and this will be active low signal. These are the modes of operation of SPI. So master and slave configuration has been implemented, and this is a baud rate is maximum input and output speed. So word length will be, we are using single to 16 bits. And as we discussed, these are the 4 different types of clocks and 4 different types of phases, which we are actually, the data has been transmitting. These are the two simple phases. One is like a phase 0 and phase 1. In the similar fashion, phase 2 and phase 3 also, the waveforms will be getting right. So these are the simulation results of SPI controller with the AXI architecture, AXI on chip bus. So in the similar fashion, the handshaking signals like AW ready and W ready are getting high at the time. So for each and every particular address location, these are getting transmitted. I mean, getting high as well as low once the address has been completed. So this is like one of the simulation results of SPI controller architecture. And when it comes to the read side, as well as we discussed in the previous sections, the similar fashion has been followed for this also. The two main signals, AR valid and address read ready. So this is the simple simulation results of SPI controller. And then this is the SPI controller with the A2O architecture. Now we'll talk about the PCIe. Now, in this PCIe generation 3 has been implemented, and the data transfer rate has been 8 giga transfers per second with a total bandwidth of 32 GB per second. 16 lanes has been part of this PCIe Gen 3, and the main part here is like endpoint configuration has been implemented in this PCIe 3. So it consists of several layers like a transaction layer and a data link layer and a physical layer. And each layer will be having 2 sections as outbound and inbound with the blocks which we are having a TLP, CC, and flow control and everything. So this is the PCIe architecture which we have actually implementing in this. So this is a simple architecture which has AXI bridge logic as well as AXI slave interface. In AXI bridge logic, this register block will be acting like one is the master, and 2 different functional registers will be acting like slave blocks. And then the whole control FSM as well as different types of FSM has been implemented in this PCIe Gen 3 IP block. This is the architecture, a simple architecture of PCIe 3, and this operates in a full duplex mode. And then now if we see the packet flow, once again, this is a packet flow through the layers. So now when we see this format of the PCIe packet, the data payload will be width of a 0 to 1024 D words, and when it comes to the header part, there will be 3 to 4 D word, as well as ECRC like single bit D word, and LCRC also. When it comes to the start and end bits, these will be like a single byte. And combining header, data payload, and ECRC, the transaction layer will be formed. And then when it comes to the data link layer, the two other like LCRC and the sequence will be getting appended into that. And at the end, the physical layer, the start and end bits also getting appended. And then this whole packet will be transmitted to the on-chip. So this is the byte format, which actually implement the different types as well as different formats, and how much amount of length it should be taken care of, and what are the attributes which actually the user wants to send. And these are the different formats, as well as depending on the bus functional model which we are using. So these different formats will be varying, and this will be different for memories as well as ICs, and different attributes has been taken care with the manufacturer as well as bus functional model. And everything will be carried out to the priority encoder logic, which is actually embedded into this PCIe controller. So these are the some general features of PCIe, and we'll now look into the design features of this PCIe 3. So this is having both AXI and AXI stream interfaces, and this bridge can support maximum payload of 512 bytes, and it can support up to 632-bit or 364-bit PCIe base address registers, and one PCIe Express virtual channel, and 8 traffic classes will be having in this PCIe 3. There is a maximum data path width up to the 128-bit. So when it comes to the PCIe lane results, see these root point PCIe expression transactions, and these two will be from the input side, which is having like a 4-bit data format. And then when it comes to the endpoint side, these both signals will be depicting the output signals of a PCIe lane. So if we go deep into this PCIe results, then there are 3 different types of signals which we have actually highlighted. Whenever this user link up signal will be getting high, in correspondence to with this, the yellow line, which is like the pin description here is like AXI master saying that the transmission ready. It is ready to transmit the data. This will be getting active asserted at the same time. And then whenever this master confirmation will be completed, then the maximum payload will be getting triggered, and it will be checked. Here you can see that maximum payload will be 3 with this PCIe 3, and so the same has been depicted here. So these are the actual results with the PCIe. So PCIe with the A20 core black dark this left one is like integrated A20 core with all peripherals, and this right side one is like which is highlighted with a different color. This is the PCIe module which we are implementing in this fabless SoC. So now the last peripheral we are observing like DMA. DMA is intelligent peripheral which relinquishedly reduces the performance. So the time taken by the CPU and increases the performance. So in this actually we are implementing the 8 channels for each and every peripheral, so that the arbitration logic will be implemented depending upon the request given by the channel, and there will be acknowledgement signal from the DMA controller also. So everything goes in a FSM methodology, and it has a configuration like 8 slave. So now we'll see like this is the micro architecture of this DMA. So now in this DMA, the blocks is like IAX interface has been outside the controller, and there are 8 channels which is communicating with this DMA engine, which is having the whole main logic. like read and write operations of FSM and everything. So there is a separate a channel priority block as well as a channel priority arbitration block. So this priority of the channel will be implemented in this three modes. If it is in the normal priority, then simply it follows the round robin model. And when it comes to the high priority, so in alternate sections, the particular channel will be assigned the resource. If it is a top priority like a non-maskable interrupts and all those things, so till the end of the operation, this will be carried through. And so these are the two different modes of DMA, which is having like a giant mode as well as an independent mode. In the independent mode, the burst sizes will be independent to the read when it compared to the read and write addresses. So this is depending upon the application, whether if you are having and acquiring the multiple sleeves at one time. So one time you can do the read operation as well as a write operation. So that is the one thing which actually happen in the independent mode. Based on the burst size we are transferring, there is a buffer capacity. This is the simple example which we have taken to depict how the independent mode and giant mode will be working. So once the giant mode will be activating in this DMA controller, then if at all any write operation is not getting triggered, it will introduce the wait state for write operation. In this example, if it is a read operation, then also based upon the write, the read wait signals has been implemented. So once the controller goes into the giant mode, the burst size for the read as well as write should be same. So when it comes to again back to the normal mode, then again we can have different size of burst transfers. But this will be mainly defined by the active port which we are using. So this is the block diagram with the A2O core which is highlighted. Then when it comes to the wrapper results, the IP address locations has been taking care here. In each and every transaction, there is a IP address locations has been coming out. So if we observe like right address locations, first it is like a 0 and then it is going to the 08 as well, depending upon the data we are transferring. So if we are transferring the less data, then this handshaking signals is getting high in a very less time. Here we are transferring more data so that it will take some time. And once these handshaking signals are getting high, then that particular data will be written into the slave. So these are the results which we are observing from the read side. So the both the handshaking signals like ER valid and ER ready are getting high at the same time for each and every address which we are actually taking care of. See, once here the first transaction in this write as well as read has been working fine since the 8 locations has been coming out from the both the operation. So this is one thing. And then for W last and R last, in each and at the end of each and every transaction, this R last and W last will be getting high, so that the controller will assume that the operation has been ended and the next transaction will be going to be start. So this is the contribution from university as well as technical mentors which they have given resources and all those things for us. Dr. G. Mamta is assistant professor from the JNTVA. The technical mentors is like Ganesh and so will be open power leader in education and research. So another technical mentor is like from Hari Nagarjun, which is actually industrial person which working in a verification domain from the TCS. These are the designers and as well as the role which they have taken care in this fabless SOC design. So if at all any queries, else we can close this session. Okay. Okay. Thanks for giving this opportunity. I will be getting it. Thank you, everyone.